Welcome back. In a previous notebook, I have shown how to instantiate an instrument and how to connect it to its underlying market data and how it reacts and recalculates when they change. In this notebook, I'm going to show how to use this to calculate Greeks when the instrument doesn't provide them. Case in point, okay, I'll start with fixing the evaluation date as usual. Here is the instrument that we're going to use, a barrier option, nothing particularly fancy. And here are its underlying market data. We have the underlying value, the risk-free rate, and the volatility, 100, 1%, and 20% respectively. So I'll wrap them in quotes so that their value can be changed and changes can be notified to the instrument. Then we're going to go through a couple of hoops since this is what the engine requires. So we're going to wrap the risk-free rate and volatility in flat curves. We're going to put those curves and the underlying value in a black the engine and set it to the option. At this point, everything is ready. We can ask the option for its value, and here it is, 1.36. The value works. If we ask to option for the delta though, here it is, no joy. Well, here is the traceback from the wrappers, you don't need to look at that. The idea is in the message right here, the delta has been provided. So the engine doesn't calculate the delta, and so the instrument cannot return them when it's asked for them. So what are we going to do? Well, we're going to use, I'm sure I'm not going to say anything new to you, we're going to use numerical differentiation. The idea is that given any function, in this case the price as a function of the underlying, we can approximate its derivative by increasing and decreasing a bit the current value of the underlying and taking the slope of this segment as an approximation of the actual derivative. Here are the relevant formulas. This is for the delta, so the first derivative, this is the second derivative, so the gamma. And as I said, nothing new. The point I wanted to make though in this notebook is that thanks to the framework that we set in place in QuantLib and thanks to having wrapped the market data in quotes as I did here, we don't have to go through the whole recalculation, the whole setup to perform these new evaluations. We just have to perturb the quotes and ask the option for a new price. For instance, okay, let's start by the current value of the underlying. Let's take 0.01 as a small change. I'm going to ask again the option for its current price, and this is our baseline. And then, as I said, I'll just set the quote a new value, so U0 plus the small increment, and ask the option for the MPV again. This is our price, this is P minus, is the same, just with the small increment becoming a small decrement of the underlying, and then we clean up by setting the quote to the original value again. As you say, well, as you expected, I hope these values are a bit changed with respect to the original one. So at this point we just translate these two formulas into code, and we can calculate delta and the gamma of the option. Here they are. This approach is not limited to delta and gamma. It can be used for any Greeks, either with this two-sided formula in which we evaluate the price at incrementing and decrementing the underlying variable, or if the calculations are expensive and you want to minimize them, with this one-sided formula. So I'm going to use this one, and as an example I'm going to calculate rho and vega of the option. I'll just repeat the calculation for the risk-free rate, so original value, small increment 1 basis point, set the new value and ask the option for its NPV. And here is the one-sided formula, so this is the rho. Same thing gives us the vega if I perturb the volatility, and here it is. The odd guy out here is the theta, not because the idea is any difference, but just because the current time is not in a quote, is not possible to wrap it in a quote. Instead, we have this concept of the evaluation date in QuantLib. So if we want to calculate the theta, what we do is just to set the evaluation date to tomorrow, and then ask the option for a new price. Is going to react just the same, and this is because, let me go back a bit here, I've set up the curves so that they move, the reference date moves with the evaluation date. And this doesn't only work with flat curves, but with any kind of curve. We might see that in a later notebook. So, as I said, evaluation date set to tomorrow, new value of the option, as I just converted this 1 day in a time increment by divided by 365, and with the same one-sided formula used before, here is our evaluation of the theta. Okay, I guess this is all for this notebook. Thanks, and see you next time.